Hello everybody. Today I would like to introduce to you intelligent monitoring of occurrence of noxious stimulation during anesthesia. We will cover the following parts. First, let me briefly introduce our study subject, HRV signals. This figure refers to a typical ECG waveform consisting of an initial P wave, the main QRS complex, and then a trailing T wave. The RR interval means the time between the R waves in two QRS. The picture below illustrates how ECG and RR intervals typically change for a normal subject at rest over about 60 seconds. So you see, this is called an HRV signal. In this study, our signals are mainly collected from 60 patients. A total of 182 signals are collected, including 78 signals of the consciousness and 104 signals of the general anesthesia. These data are divided into 3 sets, including training set, validation set, and test set. So that's what we are studying. Next, let me introduce our strategies for solving the following problems. To conduct anesthesia monitoring, we need to distinguish the consciousness and the general anesthesia. At the same time, there may be noxious stimulation during anesthesia, and this is exactly what we need to detect in time. We mainly have 2 steps. First, we use data processing and feature extraction. Separate the consciousness from the general anesthesia. Then, we further extract the features of the anesthesia signals to find out whether there is a noxious stimulation. Here, we use LSTM network to classify the states. For feature extraction, we mainly adopt EMD and sliding window method to determine the features. HRV signals can be decomposed by EMD to obtain component signals of different frequencies. Through this way, we can obtain a set of IMF signals and residual. We conduct spectrum analysis of IMF signals to get the frequency distribution relations of each IMF. Since HRV signals reflect the regulation of autonomic nerve system, the sympathetic and parasympathetic nerves of the autonomic nerve system mainly correspond to high-frequency components and low-frequency components. In this way, IMF signals can be reorganized to obtain corresponding signal components and the residue. They represent the high-frequency component signal, the low-frequency component signal, and the residue, corresponding to the average heart rate, respectively. Let's compare the features of typical signals in different states. First of all, the HF signals are relatively active in the consciousness states. The anesthesia is relatively stable. The LF signals in the anesthesia states are stable. But when there is a noxious stimulation, it is going to have more traumatic changes than when it's awake. And this is the typical features that we use to distinguish the different states. Based on EMD, we have simplified some steps, and these steps can still achieve good results, because what we really need is the features of the HF component and the LF component. We are just dividing the signal into two signals that correspond to fast and slow autonomic changes to obtain the results. The sliding window approach is mainly used to extract the features of the noxious stimulation. We can see that the LF signal has obvious sharp signal fluctuation when the noxious stimulation occurs. And we use the sliding window to capture this feature. The size of the window is generally based on the target objects and the guidance of the pre-knowledge. The window size should be basically the same as the time required for the regulation of the autonomic nervous system. This allows us to find out whether noxious stimulation occurs under anesthesia. Finally, let's see what we have got. We randomly assign the data 10 times to test our results. The final accuracy of our proposed model is about 90% when using the raw data. The results are only about 60%. It suggests that the accuracy rate of consciousness and anesthesia is high, while the accuracy rate of noxious stimulation is relatively low. However, the overall accuracy rate of our proposed model is greatly improved. This proves that our study is, in fact, very effective. That's all for our demonstration. Thanks for listening.